Today we're going to look at how we can use exponential and logarithmic functions to model some financial applications. And we're going to begin by looking at a very important formula. So this is the compound interest formula. And the formula says A equals P times 1 plus R divided by N, all to the power of N times P. Now it's important to understand what each of these letters, what they represent. So this A is our final amount. P is the principal. This is a technical name for the initial amount. So initial amount. R is the interest rate. So the interest rate. And it's important to remember that even though interest rates are often spoken of as percentages, mathematically we need to use the decimal, not the percent. N is the number of compounds per year. So interest is a percentage of the principal that's earned over an amount of time. When this interest is added to the principal, it's called a compounding. So let's say I have $100 in a bank, and over 1 year, I earn $1 in interest. That's 1%. If I'm compounding that annually, I would now have $101, and 1% of that amount is $1.01. Now that doesn't seem very big, but this was a very small example, just to show that the principal changes whenever we compound. So we could compound annually, semi-annually, quarterly, monthly, daily, even continuously. But if we compound continuously, we get a different formula. We'll talk about that next. Finally, T is our time, and it is always expressed in years for these financial applications. If you need to write this down, pause the video. In a moment, I'm going to erase it so we can do our first example. All right, so I have notes off to the side because I didn't want to have to plug things into my calculator while filming. It just wastes time. So we are going to consider an example. A student is investing $100 in an account that has 13.4% interest rate, and it's compounded monthly. And we want to know what the amount is after 20 years. Now, a lot of these questions come down to identifying our variables. So if we invest $100, this would be our principal. If our interest rate is 13.4%, we need to convert this to a decimal. So it's 0.134. If it's compounded monthly, how many months in a year? 12. And then our 20 years would be our time. All we have to do is plug this into our formula. So A is equal to the principal, $100, times 1 plus our interest rate R. So R is 0.134, all divided by N, which is 12, all to the power of 12, that's N, times T, which is 20. Now we could simplify this and break it down step by step, but most calculators will allow you to input it all in one line. And when we do that, we find we have approximately $1,437 in this account after 20 years. Even though we started with just $100. Now, it's important to realize 13.4% is incredibly high interest, and it's unlikely you would find any account that offers that much, but it does show us how powerful compounding interest can be. So let's look at that other example in which I said we would compound continuously. And we have a similar but different equation for compounding continuously. So continuously compounding interest is given by the formula A equals the principal times E to the power of R times T. Now these variables represent the same things that they represented before. We have our amount, our principal, our interest rate as a decimal, and our time in years. What's different is that instead of that big messy thing in the middle there, we just have E. In fact, it was modeling financial applications that was one of the first ways in which we understood what the number E is actually equal to. So let's get into our example. Let's say we deposit $500 into an account. This is our principal. And the account pays 5.6% interest compounded continuously. So this means R is equal to 0.056. We always need to convert it to a decimal or we will get seriously wrong numbers. Lastly, the question is how long until we have $10,000? Now I have a feeling I'm going to need some more space than this. So again, if you need a moment to write this down, hit that pause button. Now we're gonna erase this and start up top. So we're told the final amount that we're interested in is $10,000. And recall that our principal was $500. And we know the interest rate was 0.056. And we want to find the value for t. Now we've solved similar exponential equations, so all we have to do is follow the steps through. Let's begin by dividing both sides by 500. 10,000 divided by 500 is not 200, but 20. And then we have t, 0.056t. Now we do this, convert it into log form. So we have the natural log of 20 equals 0.056t. Lastly, we divide both sides by this coefficient. So t is equal to the natural log of 20 all divided by 0.056. Now, if we were just solving an equation, it'd be all right to leave this in an exact form. Since we are answering an applied question, we should convert this to a decimal. And so this is approximately equal to 53.5. But it's important to remember, what does this number represent? So notice that we're solving for t, and what are the units on t? Well, for a financial application, the units are always years. So the answer to the question of how long until we have $10,000 with an initial investment of 500 is 53 and a half years. Now it might seem like a long time, but if we think about it, we're going from $500 to $10,000 just by slowly getting that interest piled on top of each other for 53 and a half years. Now, hopefully, this is an investment, but if it were a loan and we weren't making payments, it can balloon really quickly. So it's important to keep in mind that not only do investments, but also debt and loans can grow exponentially if we're not staying on top of it. So these have been some examples of financial applications of exponential and logarithmic functions.